All right, let's dive headfirst into one of the most fundamental, and let's be honest, one of the absolute weirdest ideas in all of physics, the quantum wave function. And trust me, this isn't just about little particles. This is about peeling back the fabric of reality itself.
Just let that sink in for a second. What if everything you think of as solid is, before you look at it, just a ripple of pure mathematical possibility? It's a question that completely breaks our everyday intuition, but it's exactly where quantum mechanics leads us. So let's go find some answers. For centuries, physics was, well, it was comfortable. It was a clockwork universe. If you knew where a ball was and how fast it was going, you could predict its entire future, guaranteed. And then quantum mechanics showed up and just tossed that entire rulebook right out the window.
And this really lays out the two worlds. On one side, you've got the classical particle. It's like a tiny, predictable billiard ball. You know where it is, you know where it's going, simple. But on the other side, that's the quantum reality. Before you measure it, that particle isn't a point at all. It's a haze, a cloud of pure probability. Certainty is just gone, replaced by the laws of chance. So if a particle isn't a tiny little dot before we look at it, what in the world is it? Well, this is where we meet the absolute rock star of quantum mechanics. It's described by something called the wave function, which we represent with this cool Greek letter psi. So this is it. The wave function is basically the master blueprint of a quantum system. But here's the catch, and it's a big one. It's not something you can touch or see. It is a purely abstract mathematical object. And to make it even stranger, it's complex valued. That means it relies on imaginary numbers. Yep, the square root of -1 to fully describe how particles behave like waves, a property called phase that is absolutely essential for explaining real quantum effects.
And this is maybe the biggest hurdle to get over. When I say wave, I know you're picturing waves on a lake or sound waves moving through the air. We have to get that image out of our heads. The wave function is not a physical thing waving through the space we live in.
So what is it a wave of? It's a wave of pure information. Think of it as a wave of possibility. Every point on this wave tells you something about the probability of finding the particle at that location. It's like a weather map for existence. So let's bust a couple of huge myths right now. First, people say the electron is smeared out. Nope, the electron isn't smeared like jam on toast. When you finally find it, it's a single point. It's the probability of finding it that's spread out. Second, this wave doesn't really live in our cozy 3D world. For a system with lots of particles, it exists in some wild, high-dimensional mathematical space that just keeps track of everything that could possibly happen. Okay, so we've got this ghost in the machine, this abstract wave that uses imaginary numbers. How on earth do we connect that to the real world, to things we can actually measure in a lab? How do we crack this code?
I mean, that's the whole ball game, right? If this psi thing is fundamentally unseeable and packed with imaginary numbers, how does it ever give us a real-world probability, a number between 0 and 100% that we can actually test?
Well, the answer came from the brilliant physicist Max Born, and his solution is just beautiful. It's a simple three-step recipe. You start with the wave function itself, which we call the probability amplitude. Then you apply a special procedure called the Born rule. And what pops out on the other side is the probability density, which is the actual measurable probability we're looking for.
And this is the secret decoder ring. The Born rule tells us you don't use the wave function directly. Instead, you take its magnitude and you square it. This little mathematical trick, multiplying the function by something called its complex conjugate, is genius because it magically gets rid of all the imaginary parts and guarantees that your answer is always a real positive number. Physics needs probabilities to make sense, and this is how the math delivers.
But there's one last rule of the road. It's a rule that keeps this whole system honest, that anchors it in reality. It boils down to one simple common sense fact. The particle has to exist somewhere. This is what we call the normalization condition. All it's saying is that if you take the probability of finding the particle at every single possible point in the entire universe and add them all up, the grand total has to equal exactly 1. 100%. I mean, of course it does. This scary-looking equation here, that's just the fancy formal way physicists say, yep, we're guaranteed to find the particle somewhere. So, now we have our toolkit. We have the wave function, and we have the rules to translate it. So let's use them to explore where things get truly, truly strange. Before we look, a particle is in what's called a superposition.
This doesn't just mean it could be here or there, it means it is, in a very real way, here and there and over there and everywhere else it could possibly be, all at the same time. The wave function is the perfect mathematical sum of all of these coexisting realities. So that's the bizarre before picture. But what happens in the exact instant our measurement interacts with the system? Poof! The wave of possibility collapses. In an instant, that entire cloud of maybes just vanishes, and the particle snaps into reality at a single, definite location. The many possibilities become one single fact. And which fact does it choose? It's completely random, with the odds of landing in any one spot perfectly dictated by the Born rule we just talked about.
So, let's just step back for a second and try to wrap our heads around all this. What's the final takeaway? What is this strange mathematical ghost really telling us about our universe?
This, to me, is the most profound insight. The wave function isn't a blurry, incomplete picture because we're not smart enough to see the real picture. No, it is the complete picture. It contains everything that is possible to know about that system. And left on its own, it evolves perfectly and predictably according to the Schrödinger equation. The weirdness, the randomness, only kicks in when we interfere. The universe, at its very foundation, is not a machine of certainty. It's a system of pure, evolving probability.
And this quote just says it all perfectly. It's not a wave of stuff, it's a wave of information, a wave of potential. It holds the complete story of everything a particle could be, right? Right up until the moment reality forces it to pick just one path. And that really leaves us with the big one, the question to ponder. If reality isn't a clockwork machine, if it's built on a foundation of pure probability, a cosmic dance of mathematical chance, what does that actually say about the world we think we know? What is reality really?